function. So if they give you directions and it just says analyze this function, draw its graph, they want you to go through all 8 of these steps. Sometimes they walk you through it and they say do this, do this, do this, but otherwise make sure that you know you can find every one of these little components. So I've pulled 3 examples and I'm going to go through each of these parts with you. So maybe have your book open so that you can keep this in front of you. And let's see. So here's my function. R of x is 2x plus 4 over x minus 1. Okay, step 1. Let me get my pen. All right, so step 1 says factor the numerator and the denominator of r, figure out the domain of the rational function. Okay, so look at it. Only thing I see here is I can pull a 2 out of the numerator. Okay. But that's really all I can do as far as factoring this one. Okay. Go ahead and figure out what the domain is. And remember, with a rational function, you are worried about the denominator equaling 0. So you look at that and you say, wait a minute, x better not be 1, right? So in set builder notation, set of all x such that x cannot be 1. You certainly can do it in interval notation as well. Okay. Step number 2 says write r in lowest terms. Well, what that means is if there's any common factors on top and bottom, then you would reduce those down to 1. You cancel those out. There's nothing common on top and bottom of this. You've got a 2 and an x plus 2 on top. You've got an x minus 1 on bottom. Nothing's going to cancel. So as far as you're concerned, nothing to do in step 2. It's already in lowest terms. Okay. Step 3. Find the intercepts of the graph. Okay, so how do you find the intercepts? Let's see. You find the y-intercept by putting in 0 for x. And so you get 2 times 0 plus 4 over 0 minus 1, which is 4 over negative 1, which is negative 4. I'm going to go ahead and plot that on my little grid over here. Okay. To find the x-intercepts, you set the function equal to 0. And remember, when you're dealing with rational functions, the denominator cannot equal 0 because that's where we get the undefined, we don't want that happening stuff. Okay, so the only thing that can make a fraction equal 0 is the numerator. If you have pieces connected by multiplication equal to 0, then one of the pieces is going to be 0. 2 is not going to be 0 though. So the only x-intercept is negative 2. And I'm going to go ahead and plot that. Okay. All right, so step 4 says determine the vertical asymptotes. Graph the vertical asymptotes as dotted lines. Okay. So the vertical asymptotes, if you go back to step 1 and you think about your domain, and you look at the denominator, okay? Also check out step 2. As long as it's in lowest terms, anything that makes the denominator equal to 0 gives you the vertical asymptote. So 1 makes this denominator equal to 0. We better not have any point on the graph that has an x value of 1. So we say that we have a vertical asymptote at x equals 1. If we happened to have had a factor that would cancel in top and bottom, then what we would have had would we have a little baby hole in the graph. It would look just like a normal graph, except at that one little point, you'd knock a hole in it and put an open circle. Okay? But since this was already in lowest terms, whatever makes the denominator equal 0, we know we can't have that as our x value. So we put this vertical asymptote thing on the graph to remind us, don't you dare draw a piece of this graph with that as an x value. 5. Determine the horizontal and oblique asymptotes. Draw them and figure out if it happens to cross them. Okay, so now do you remember how to find horizontal and oblique asymptotes? You go back and you look at the degree. Okay, look at the degree of the numerator and the degree of the denominator. And you had a little theorem that told you that if the degree of the numerator was smaller than the degree of the denominator, then the horizontal asymptote is the x-axis. If the degree of the numerator and the degree of the denominator are the same, which is what we have here, they both have degree 1, then to get your horizontal asymptote, you make a fraction out of the leading coefficient. So horizontal line, y equals, and then your leading coefficients are 2 over 1, or 2. Okay, so if the degree on top and degree on bottom are the same, make a fraction of the leading coefficients. Here, 2 over 1 is 2. Okay, so that's your horizontal asymptote. And I'm going to draw it with another dotted line. I'm making this one green because it's possible that there is some point on the graph that goes through that dotted line, the green one, the horizontal one. Not at all possible to draw through the red one, okay? But it's possible that there might be some point that has a y value of 2 on this graph. So I need to stop and check that. Okay? And the way I check that is I substitute 2 in for y, and I see if I can solve for x. Notice how I went back and I used the one from the very beginning, the one that's not factored. Totally personal preference. You certainly could have gone to step 1 and used this one. I just chose to do it this way. Okay. Plug 2 in for y, see if you can solve for x. Okay. If I multiply both sides by x minus 1, because I already know I can't have x equal to 1, multiply both sides by x minus 1. And then clean it up and see what happens. Let's see. So 2x minus 2 equals 2x plus 4. If I subtract 2x from both sides, they cancel out, and I get minus 2 equals 4, which doesn't make any sense at all. Okay, so what this says to you is it doesn't intersect the horizontal asymptote. Okay, if it was going to intersect the horizontal asymptote, I would have been able to solve this, and I'd get like x equals 1/2 or x equals 7. Okay, and that would tell me exactly where to let it cross the horizontal asymptote. But here it doesn't cross. Okay, now step 6, 7, and 8. So 6 is use the zeros of the numerator and denominator to divide the x-axis into intervals and test points. Step 7, analyze the behavior of the graph near each asymptote and indicate this behavior on the graph. Okay. I like to put this together and think for a second. Remember multiplicity? Remember that? That was the idea that you could look and see how many times you get a specific x-intercept. And depending on whether it was an even number of times or an odd number of times, it told us whether it crossed the x-axis. So like if we had an x-intercept that had an odd multiplicity, we knew it had to cross the x-axis at that x-intercept. We knew that if we had an x-intercept with an even multiplicity, it had to just touch the x-axis there. That's going to save us here because it'll help us a lot. So if you look down at the graph, you've got this x-intercept and you've got this y-intercept. The multiplicity of the x-intercept, if you go back over here and look, okay, the multiplicity is 1. Okay, you only got it once, the degree was 1. So that means it's going to cross the x-axis at -2. Now, I got choices. It can either go this way or it can go this way. One of those two options, right? Well, the way, let me get that off there. There we go. The way I like to think about it is, what can it not do? You know, for instance, if I tried to make it do this, well, that doesn't make a lot of sense because my y-intercept is way down here somewhere. And I need to be able to connect my y-intercept and my x-intercept. So There we go. All right. So it makes sense that these are going to have to be connected like this, right? And if the multiplicity of the x-intercept says it's got to cross the x-axis at -2, I'm thinking the only choice I've got is for it to do this. Right? It can't hook back around to the right, then it wouldn't be a function. It's not going to turn around and go back down because there's not another x-intercept over to the left. And the whole point of that green dotted line is to tell me what the graph does as I draw it off to the side, and it can't cross it either. Okay? And kind of the same idea here. If this is my y-intercept at -4, pretty much only thing it can do is that. It can't hook back over. It's got to be a function. It's got to pass a vertical line test. So I'm pretty much stuck. Okay. All right, so now think. The domain of this thing is all real numbers except 1, which means you need to have this graph drawn everywhere except at that little bitty dotted red line. Okay, x = 1 is the only place where you will not have an x value. Okay, so you've got to have something over to the right of the dotted red line, and your choices are either it's going to have to go like this, or it could go like this. Can't do both. Can only do one of them, and you pretty much already know which one it's going to be. Okay, because if you think about it, it can't be the blue one because we don't have an x-intercept there. Okay, it's got to be the pink one. All right, so if you want to find out exactly where it goes up in that top corner, you could plot a point. Like for instance, I could do, let's see, 2. Suppose I want to find r of 2. Okay, so it'd be 2 times 2 plus 4 over 2 minus 1, which is 8 over 1, which is 8. So at 2, the y value is 8. That's up here. Sorry that it went off my grid. Okay, you can always do that. You can always plot points if you want to. Okay, let's try r of 3. So 2 times 3 plus 4 over 3 minus 1. 6 plus 4 is 10 over 2, which is 5. So at 3, the y value is 5. So that helps a little bit. Okay, I knew it was up there at the top, but this gives me just a few more points. You can always plug in 4, 5, 6 if you want to. But what we're after is that the graph has to be up in that little part. Okay, plotting points is perfectly fine. I just think that it's better to think about the things you already know first. Use the information you know about multiplicity. Use the fact that you know where you do and do not have intercepts. And then plot points as you need to. Okay. All right, let's do another. All right, so let's try this one. Okay, we're just going to go through all the steps again, following what they tell us. Step 1, factor the numerator and denominator. Write the domain. Okay, so what does that factor? So that x minus 3, x plus 2. Okay. All right, and domain. All x values except you can't use 3 and you can't use -2. Oops, sorry. Okay, whatever makes the denominator 0. Okay. All right, step number 2 is this thing in lowest terms. That means check and see if there's anything that you can cancel on top and bottom. You know, anything that will divide to give you 1. And here there's nothing, so it's already in lowest terms. So that says to you right then, you already know that you're going to have vertical asymptotes at 3 and -2. Okay. If there had been a factor that you could cancel on top and bottom, then again, that's the condition for having a hole. Okay, so it's in lowest terms. Step 3. Find the intercepts. All right, so again, you find the y-intercept by putting in 0 for x. And you get 6 over negative 6, which is negative 1. So you have a y-intercept at negative 1. You find the x-intercepts by setting it equal to 0. Remember, the only thing that can make a fraction equal 0 is its numerator. Its denominator can never make it equal 0. Okay, if a fraction is going to equal 0, that's going to come from the numerator. Well, here 0 equals 6. That doesn't make any sense. That's not going to happen. This thing has no x-intercepts. So it's only got the one y-intercept at negative 1. Okay. Vertical asymptotes is step 4. We already figured that out as soon as we found out what the domain was and the fact that it was in lowest terms. I have a vertical asymptote at 3 and another vertical asymptote at negative 2. And these are my equations of the vertical lines. Okay, vertical asymptotes are vertical lines. So I have one at 3. And I have another at negative 2. I'm drawing them in red to remind myself not to dare draw any piece of that graph through those red lines. The minute you put the vertical asymptotes on there, you can see that this graph is going to be in 3 pieces. You're going to have a piece of the graph to the left of negative 2. You're going to have another piece of the graph between negative 2 and 3 in that middle part. And you're going to have another piece of the graph to the right of positive 3. Okay. So step 5. This is where you're doing the horizontal or oblique asymptotes. So you go back over to your function. And you look and see. You're looking at the degree of the numerator and the degree of the denominator. Okay, so the degree of the denominator is 2. The degree of the numerator, 0. So the degree of the numerator is smaller than the degree of the denominator. And our theorem told us that whenever the degree of the numerator is smaller than the degree of the denominator, that means that we have a horizontal asymptote at y equals 0, or the x-axis. Okay. Then you're supposed to figure out if there is any point on the graph where you cross the horizontal asymptote. Well, it's real convenient because we've already found the x-intercepts and we've already found out there are no x-intercepts. So the graph does not intersect the horizontal asymptote. Okay. Then 6, 7, and 8. Draw the thing, right? Again, think about multiplicity. Okay. Now, we don't have any x-intercepts. We have vertical asymptotes. Do you see how you got this factor here one time and this factor here one time? So just like when you talked about the multiplicity of the x-intercepts, if it was an odd degree, we knew it crossed the x-axis, it changed signs. If it was an even degree, we knew it didn't change signs. It's either bounced on the top or it bounced on the bottom. You can think about it kind of the same way with the vertical asymptotes. If the degree of the vertical asymptotes is odd, it's going to run down on one side and up on the other. And I'll show you what I mean. Okay. All right, so go look at the graph. And the first thing I think of is if I'm looking at my y-intercept here, and I know I'm supposed to run beside the red vertical asymptotes, and I can't cross the green one, then it says to me that pretty much all I can do is something like this. I can't go up on either side because I can't cross the dotted green line. I've already checked that. That's what this checked for me. I don't have x-intercept, so I can't cross the x-axis. Okay? So if you've looked at this piece with the multiplicity, and you see that it's running down on the right-hand side of the vertical asymptote at -2, what that says to you is it has to go up on the other side. Okay, so it's going to go something like this because that's all it can do. You are welcome to plot points if you want to. You can take and plug in, say, -3. And so you get 6 over -3 minus 3 times -3 plus 1, which is 6 over -6 times -1 is 6, which is 1. So at -3 it's 1. Okay, so I didn't pull this down far enough. Let me get that down further. Okay, so I'm going to go like this. Okay, so still in the same idea, okay? Do the same thing over on the other side. It's running down beside the vertical asymptote at 3. If its multiplicity is odd, if it's running down on one side, it must run up on the other. Okay. Do the same thing if you want. Plot a point just to figure out how tight it goes in that little corner. Maybe check 4. So 6 over 4 minus 3 times 4 plus 2 is 6 over 6, which is 1. Okay, so that one there. Okay, same deal. Runs up there and down like that. Okay. Want to try one more? Okay. How about this one? Step number 1, factor it and figure out what the domain is. Do you recognize the numerator? The x to the 3rd plus 1? That's a sum of cubes, right? Factors into x plus 1, then x squared minus x plus 1. That's your formula from way back in the appendix about factoring a sum of cubes. If you don't remember that, be sure you go back and look it up. On the bottom, I can pull out an x. So my domain, set of all the elements x such that, let's see, x can't be 0. And x cannot be -2. Step 2. Is it in lowest terms? And yes, this one is too. I didn't mean to pick all 3 examples that are in lowest terms, but it just so happened. It's already in lowest terms. Okay, step 3. Find the intercepts of the graph. Okay. So, to find the y-intercept, you put in 0 for x. So I'm going to use the one that's not factored just to make it a little bit quicker. 0 plus 1 over 0 plus 0. That doesn't work, does it? Okay. Remember, x can't be 0. Okay, so there is no y-intercept. To find the x-intercepts, remember you set the fraction equal to 0. And remember, the denominator is not going to help you here. The only thing that can let this thing equal 0 is the numerator. So x plus 1 is 0. That would give you -1. X squared minus x plus 1 equals 0. What does that do? I don't think it factors. Might give us some irrational x-intercepts. So we better do quadratic formula. So -1 plus or minus the square root of -1 squared minus 4 times 1 times 1 all over 2 times 1, which is 1 plus or minus the square root of -3. That's not real. Okay, so if it's not real, it can't be on our graph because we are plotting real numbers. Okay, so our only x-intercept is at -1. We have no y-intercepts, and we only had that one x-intercept. Okay. All right, 4, that's our vertical asymptotes. Those are the values that make the denominator equal to 0. They came from the factors that you couldn't reduce on top and bottom. So there's one at 0, and there's one at -2. And that one's hard to see, but we'll put it on top of it. Okay, so like that. All right, now, step 5. Does it have a horizontal or an oblique asymptote? So check the degrees. The degree of the numerator is 3. The degree of the denominator is 2. So if the degree of the numerator is bigger than the degree of the denominator, then that means you're going to have an oblique asymptote. That just means a slanty line. Okay, so how do we find the oblique asymptote? That's where we have to do long division. Okay, so I need to divide x squared plus 2x into x to the third plus 1. And I got to do it by long division. And I'm going to make sure I don't mess anything up. I'm going to put in these missing terms with a 0 as the coefficient because I don't want to mess it up. So what I'm after is the quotient. Remainder doesn't matter to me. Whenever I want to find an oblique asymptote, I'm after the quotient. How many times does the x squared plus 2x go into the x to the third plus 1? Okay, so x squared goes into x to the third, x times. I multiply x times x squared is x to the third. X times 2x is plus 2x. I subtract. I change the signs. So 0x squared minus 2x is minus 2x squared, sorry. 2x and yeah, squared, forgot my squared. And then I bring down the plus 0x. Okay. Then I divide x squared into -2x squared goes -2 times. -2 times x squared is -2x squared. -2 times 2x is -4x. I subtract, I change my signs. So 0x plus 4x is 4x. I bring down the plus 1. Well, x squared is not going into that. So this is my quotient. So my oblique asymptote is y equals x minus 2. Okay. So I'm going to draw that with a dotted line. Okay. Y-intercept is -2, slope is 1, so I can draw this really quickly. So my y-intercept is at -2, slope is 1, and I'm going to draw this in with a dotted line, because again, this is a guide to tell me what to do with the graph as it goes off to the sides, way off to the left and way off to the right. It is possible to cross an oblique asymptote. So you have to stop and check it, okay? You have to see what happens, just like when we did with the horizontal asymptote. You have to take and set the original function equal to the x minus 2. This is getting really cramped in here. Okay, so x minus 2 equals x to the third plus 1 over x squared plus 2x. Okay, just like for the horizontal asymptotes, we set it either equal to 0 or equal to a number and solved it to see what happens. Well, this time we set it equal to the line x minus 2 to see if there's a point where these intersect. Okay. I already know my domain. I already know I can't use 0 and -2. So I'm going to cross multiply. I'm going to get x minus 2 times x squared plus 2x equals x to the third plus 1. Got to multiply that out on the left. So let's see, x to the third plus 2x minus 2x minus 4x. What did I do? Wait a minute. X to the third. Then plus 2x minus 2x squared. There we go. Those are my x. I keep forgetting my x squares. Sorry, I just said that totally backwards. X times x to the square is x to the third. X times 2x is 2x squared. Negative 2 times x squared is negative 2x squared. And negative 2 times 2x is negative 4x. Okay. Equals x to the third plus 1. Phew. This reduces with this. I've got x to the third minus 4x equals x to the third plus 1. If I subtract x to the third from both sides, subtract out to 0, I got negative 4x equals 1. So x is negative 1/4, or negative 0.25 if you want to do it as a decimal. Okay, so when x is negative 1/4, this thing crosses the oblique asymptote. So probably going to be, what, right around in here? Does that look right? Okay, let's see. Plug in negative 0.25 into the original function. Let's get that y value. So g of negative 0.25. If you plug that in, I get negative 2.25. Okay, oops, I put my little blue dot in the wrong spot, didn't I? It's supposed to be negative, isn't it? It's supposed to be negative, oops, negative 0.25, and negative 2.25 is where it crosses the green line. So negative 0.25, it should be right here. Okay, so that's the only place that I can draw my graph through the green line. Okay, so let's see. Steps 6 and 7 and 8 say plot points. Okay. Before I get into that, I'm going to think about what I already know. I'm going to go to that part that's in the middle, in between the two asymptotes. I know I need to be able to connect the black dot, which is the x-intercept, with the blue dot, which is the point I found where it crosses the oblique asymptote. Pretty much got this. And so it makes sense to me that it's going to have to continue down like that and up like that, because there's really nothing else it can do. Okay. So if you go back and you look at the multiplicity of the vertical asymptotes, notice that the multiplicity on both of them was a 1. So that says to me that if it runs up here, it should be running down on the other side, which makes me think it's down here somewhere. Okay. If it's got to run down and then it can't cross the green dotted line, I mean, all it can do is some sort of U thing down there at the bottom. Okay, and then the same thing over on the right-hand side of 0. If it's running down on the left-hand side, it needs to be running up on the right-hand side. So again, it's going to be doing something like this. Sorry, it should be running it more smoothly that way. Let's check some points though. Let's be sure about it, okay? So let me get that off of there. Let's check a point and get it exactly where it needs to be. How about, I'm going to check 1. Okay, so let's see. So we need to check, sorry that I'm just squeezing this in here, g of 1. We get 1 plus 1 over 1 plus 2. What's that, 2/3? So right around in here, like so. I need to calibrate my... And you could do the same thing with the one down on the bottom. You could check a point. You could plug in, say, -3 and get it in there real exactly. I'm not going to do that just a second. I'm going to calibrate my pen to make sure it's drawing where I want it to do. So hang on just a second. Okay, I think I got my pen calibrated now. All right, let's try going in the other direction. Suppose I give you a graph of a rational function and I say, hey, can you give me an equation? Lots of possible answers. There's not one set way to do this, but there are some things that are common that we can look at. Okay, first of all, it's a rational function. R of x, f of x, whatever you want to call it. Okay. First thing I would do is I would go looking for my vertical asymptotes, and we have one at -3 and we have one at +4. And that says to me that if x can't be -3, that there must be a factor of x plus 3 in the denominator. And if there's a vertical asymptote at x equals 4, that says to me there must be a factor of x minus 4 in the denominator. Okay. All right, so now, what else do you see? What else would help? Okay. What about x-intercepts? Do you see any x-intercepts? That's hard to see on there, can't you? I think right there at -2 and right there at +1. So same kind of idea. If -2 is an x-intercept, that means it's a place where the graph equals 0, so it's a factor of the numerator. X minus 2 comes from the factor x, the x-intercept of -2 comes from the factor x plus 2. The x-intercept 1 comes from the factor x minus 1. Okay. And all right, now what? Where does this come into play? If there's a horizontal asymptote at 3, the only way I can get a horizontal asymptote that's not on the x-axis is if the degree of the numerator and the degree of the denominator are the same. Okay, well that's cool. I got 2 on top, I got 2 on bottom. So my leading coefficients have to do a ratio that equals 3. So I'm going to put 3 over 1. Could put 6 over 2. Anything that reduces to 3. I'm just going with 3 over 1 because that's the easiest. Okay. All right. Now let's check. Look at this x-intercept. Can you see? It's little in there, but can you see that it bounces? Can you see that it bounces right there? It crosses at this one, but it bounces at this one. So that says to me that the multiplicity of that x-intercept has to be even. And right now that is not what I have. Okay? It says to me that this has to be a 2, a 4, or 6, or some other even number. Okay? And then the minute I do that, the degree on top is 3, degree on bottom is 2. Well, that screws up my horizontal asymptote. So now I'm going to look at my vertical asymptotes and let's see. Okay, here it goes up on this side, down on this side. Okay, but see at this one it goes up on both sides. That says to me the multiplicity of that x-intercept needs to be even too. So again, 2, 4, 6, 8, whichever number you want, I'm going with the smallest. Alright, so does this work? I have a horizontal asymptote at 3. Yes, that would work. I've got my x-intercepts at -2 and 1. Odd multiplicity on the -2, even multiplicity on the 1. Vertical asymptotes at -3 and 4. Even multiplicity on the 4. This is cool. This will work. Okay. I can also plot a point if I need to. I can pick some point that I know that's on the graph and test it and see, but this is pretty cool. Okay, there's more than one answer that's possible. This one works just fine.